Good morning, everyone. Thanks a lot for being here. Let me start by reminding ourselves what we've done last time. So last time I tried to explain this large deviation principle. At least I gave you a possible mechanism for figuring out large deviations for a sequence of random variables. And also, very briefly at the end, I tried to gesture that there is this notion of Gibbs measure that makes sense for physical systems in general. I tried to give you intuition for why it makes sense from a physics perspective, but it's also meaningful to look at it even from a purely mathematical point of view. Like, it's a very natural object, and we see that it enjoys interesting properties that we can study with analysis. Today I want to give a brief reminder or presentation of basics of statistical mechanics. So I will mostly give you a very brief overview of the Ising model first, and then of the Curie-Weiss model, which later we will try to study using these techniques using partial differential equations. So I understand that many of you already know about the Ising model, but not all of you. And even for those who already know, I'll try to emphasize aspects that will be relevant for this class. So I'll try to emphasize this free energy and what we can learn from the study of the free energy, even for the Ising model. So hopefully this will be interesting. And for the Ising model, because it's perhaps more intuitive to understand immediately why it makes sense to study it, we will see why once we understand the free energy, we can derive interesting properties that we can make sense of from our intuitive point of view. All right, so let's say that the first part is about a brief reminder or description of the Ising model. So to give a historical background, in the years around 1895, there was Pierre Curie doing experiments in his lab, and I think at about the same time also Maria Sklodowska, who later would become Marie Curie, who also was independently doing this sort of experiments. They were experimenting with metallic objects, metallic pieces of material. They observed that if they submit these pieces of material to a magnetic field, then even after they remove the magnetic field, this piece of material keeps some magnetic properties. It will keep being magnetized, as we would say, maybe. And they were intrigued by this, and they were also intrigued by the fact that when they heat up the material sufficiently, then this property disappears. The material no longer is able to retain the memory of the magnetic field it has been subject to. And so they were calling this the magnetocaloric effect, and they were trying to understand why this is happening. And well, okay, they studied this for a lot of time. In particular, the transition between being able to retain this magnetic field and towards no longer being able to retain this magnetic field as you increase the temperature. And then in the 20s, Wilhelm Lenz thought about a possible theoretical model to try to understand this phenomenon, and proposed that his student Ernst Ising study it. Okay? And the model is like this. So we imagine that the piece of material is made of a collection of atoms that we can think of as being organized on the d-dimensional lattice. Maybe d equals 3, but let's say it's zd. And so let me denote by Bn a box in the lattice of side length 2n, maybe. And a configuration for our piece of material is we think that each of the atoms has a sort of mini magnet, and it can be oriented +1 or -1. Maybe we just think of one direction of our magnetic field. And so to record the configuration of our piece of material, we have this vector of +1 and -1 indexed by the sides of this box Bn. Okay? And for each piece of configuration, we think that there is an energy associated with it, which I'm going to denote Hn of sigma, which, so yeah, in our heads we think that when the spins, so maybe I should make a drawing. So I do the drawing in dimension 2, and so at each site of the lattice, there is a little piece of magnet which wants to be up or wants to be down. So it's +1 or -1, and then we think that neighboring sites would like to align their spins. Okay, so in the energy, we're going to record that it's preferable for the system to have neighboring sites have aligned their magnets being aligned with one another. Okay, so I'm going to encode this by defining my energy like this: the sum of sigma I, sigma j, where I and j range in the box and are neighbors in the box. Okay, I'm going to write like this: I twiddle j to mean I and j are neighbors in the box. So by neighbors, I mean nearest neighbor. These two are neighbors, and the neighbors of this guy are this guy, maybe this guy who is here, and this guy. Okay, so far so good. Okay, so yeah, there's one thing I should say is that physicists would put a minus sign here because this is +1 if the spins are aligned, if sigma I is equal to sigma j, and this is -1 otherwise. So it's often more intuitive to think that the system is trying to minimize energy. If you want things to conform to our intuition, then I should put a minus sign so that minimum energy is where everybody is aligned and maximum energy is when many people disagree. But okay, I try to minimize the number of minus signs I'm writing down, so I'm not going to put the minus sign. Okay, so in my convention, the system is actually going to try to maximize the energy. Slightly, perhaps a counterintuitive move, but okay. It saves us a number of minus signs. And then we said yesterday that if we let our material rest in our room for a while, then it will be found typically in a configuration sigma with probability proportional to exponential of beta times Hn of sigma, where beta is the inverse temperature. And yeah, I should have said, yesterday I said exactly that phrase, exponential of beta times the energy. And this is again because I have this slightly bizarre sign convention, okay? Otherwise I should have said minus beta times the energy. So yeah, sorry that I did not pay attention to this yesterday. Yeah, so then yeah, we want to study the probability proportional to the probability measure, which to each configuration sigma gives weight proportional to exponential beta Hn of sigma. But in fact, perhaps a little bit like Pierre and Marie Curie, we want to also be allowed to play with this object. So we want to maybe submit it to an external magnetic field and see what happens when we do that, and see what happens when we remove it. Okay, so I'm going to add another term which captures this, which is perhaps our measuring apparatus in some sense. And yeah, I'm going to depart even further from proper physics because I'm going to encode this by just adding it like this without taking care of the beta. Okay, I'm going to add my external magnetic field like this. Okay, I'm going to add some parameter h, which is the intensity of our external magnetic field we can play with, times the sum of sigma I. So you see that, okay, if maybe I should, if I had been a good physicist, maybe I should have put this inside the definition of the energy function. And then you see the energy is getting better when the sigma i's align with h. Okay, h is, so beta is non-negative, and h is the real parameter. But mathematically, it's kind of convenient to have the two parameters like this be separated, so I'm going to set it up like this. Okay, so it slightly messes up the interpretation of beta as an inverse temperature, but okay, you could then a posteriori change variables in the h, and it's fine. Okay. Is there a question? Yes?
I could see some papers where h depends on I.
Ah, yeah. So in my
relevant or just?
Yeah, it's also interesting, but here I'm doing an easier situation where h is just something external we fix. Everybody has the same is subject to the same external field h. But yeah, thanks for the question. Are there other questions so far? So it's good. Yeah, I should have said, so this is the sum over I in the box. Okay. All right, so now we have our material. We know that it's supposed to be distributed like this. And what could we make as an observation? We could look at what happens to the average magnetization, this sum of sigma I. How does it behave under the Gibbs measure for fixed beta and H? Okay, so what we would like to study. So perhaps I'm going to first define Zn of beta and H, which will be the sum over sigma in +1 -1 of this exponential. The same exponential I'm not copying. And then one question we would like to ask ourselves, so let's say question. How does let me call this Mn of beta and H, the average magnetization under the Gibbs measure, how does this look like? So what is this? So 1 over Zn beta H, sum over sigma of, this is my observable, 1 over n, oh sorry, not n, 1 over the cardinality of the box, sum over I in the box of sigma I. Okay, I want to study this quantity under the Gibbs measure. So this is my observable, and then I write the weight of the probability weight. Okay, so exponential of beta Hn of sigma plus H sum of sigma I. Okay, maybe it's a long expression. I did not use great notation so far, but this is what I would like to be interested in. No? Does that make sense? Or yes? Yes? So yeah, maybe we could try to open our computer and simulate it just to see how it looks like for some values of beta and H, and we think of n as being large. And let me do a blackboard simulation. So okay, we fix some beta, and now I'm going to plot that function for n large as a function of H, okay, for a fixed beta. So surely when H becomes really very, very large, this will be very influential in our sum, and so we will manage to basically force this guy to be maximal. Basically, this will be everybody being +1 in this sum. Okay? So here we'll get +1, essentially. So for H very, very large, this is going to asymptote to +1. Okay, this is 1. Surely this is between -1 and 1, right? So, but when H is very large, it's going to be +1. And when H is very negative, similarly, it's going to be -1. Okay, and then there's a symmetry, so it's going to be an odd function. So surely it's going to look something like this. Make sense? But then, if I try to run another blackboard simulation for beta larger, I'm going to see that this is going to start to slope more, because we favor configurations that have all of the sigmas agreeing to with one another. So typically, this term also would like to make sure everybody agrees. So the H tilts us towards +1, but also we want to make sure all the sigmas agree. So this is maybe for small beta. And maybe if I plot the thing on the same scale for large beta, I'm going to start to see something which is very spiky like this. Okay, and this is still for finite n, so it's just the simulation I'm running on my computer. This is H, and this is large beta. And so the question arises, what happens in the limit? Is it the case that this becomes a discontinuous function? Or is it the case that it remains smooth for every beta? And now the organizers have offered us a new toy, which I am very eager to play with. Nice. Maybe I'll erase a bit of this too. All right. Very nice. Thanks a lot. So that's the question that Wilhelm Lenz asked Ernst Ising. And Ising answered the question in dimension 1, and he found that, in fact, no discontinuity arises in this curve. For beta arbitrary, even very large, even in the limit n goes to infinity, this remains a smooth curve. And people were kind of disappointed by this because if the thing had been discontinuous, they thought this could have been a good model for why for the phenomenon that Pierre and Marie Curie were observing. Because you see, it means that if you prepare your system, if there is a discontinuity, it means that really, even for an arbitrarily tiny h, your material wants to have all of its spins go into a magnetized state. Does that make sense? So there was really a hope that you could find a critical beta that captures this discontinuity that that Pierre and Marie Curie were observing experimentally in some sense. And then things remained like that for a while until I forgot his name. Rudolf Peierls, I think. Let me check his first name. Yes, Rudolf Peierls. In 1936, realized that this is only the case in dimension 1. And in higher dimension, so maybe I should have said also Ising and maybe other people expected that even though they could only do the calculation in dimension 1, they expected that the argument they were using would generalize to higher dimensions. So they were indeed disappointed. But in fact, in 1936, Rudolf Peierls realized that this was not valid, that in fact, as soon as you're in dimension 2 or higher, this phase transition does occur. So there exists a critical beta. So small beta now really means a beta smaller than some beta c, for which, until beta is below beta c, the curve is continuous. But for beta larger than beta c, if you really pass to the limit of large n, there is a discontinuity in this curve. Okay, the curve looks really like this. Whoop. Whoop. Okay, and I'm at h equals 0, it's 0, but I'm not plotting it. Okay. Forget about h equals 0. Okay, and so in the end, this beta c made sense. They could identify a critical temperature. Now this is called the critical. In physics, this is called the Curie temperature, and they could make sense of it on this toy model, and so this was much more satisfying. And then again, things remained like this for a while. And I think really what made the so maybe I'll speak about this a bit later. So let me try to describe how you can approach this question mathematically. And I'll try to emphasize this free energy thing and see how it relates to this question. So let's define the free energy the way, mimicking what I was kind of advertising in the first lecture. So I'm going to rewrite it, but this is the Zn of beta h that I was writing here. I put n, but I mean Bn. Okay, so let's define this quantity. So far, so good. So the claim is that if we understand this, then we will be in good shape to understand this quantity I was calling Mn of beta h, which is written here. The reason is that this quantity Mn of beta h is a derivative of this function. So let's verify this. If I differentiate this with respect to h, what will happen? Well, we have a logarithm, so when I differentiate, I get the derivative of this guy divided by that guy. When I differentiate this guy, this is the sum of sigma I, which is going to pop up, like this in front, like this. Okay, the 1 over the volume of the box is here, and so it matches. Okay, so this is equal to Mn of beta h. And it's much more convenient to study this function than to try to study this function directly. I hope that when you see this relationship, this starts to feel plausible, because if you try to study the limit of something, it's going to be easier for you if you study the limit, the behavior of the function rather than the behavior of its derivatives. Maybe its derivatives are more fragile, they depend on more things, etc. So in particular, yeah, like showing that this has a limit is something you can do by hand with, by like kind of first principles. It's very robust. The limit will be very robust. For those of you who quickly understand this, you know that in the box here, I did not impose any boundary condition outside of the box. So for instance, the limit of this thing will not depend on any boundary condition. It will be very stable with respect to perturbations of your system. On the other hand, this is going to be a little bit more fragile. You know that the minimization, maybe depending on the boundary condition, things will be slightly different, at least in certain points, etc. So this is a more subtle quantity. So that's why I claim that studying this first makes sense. This is what Ising did in dimension 1. And so he could compute this, but you see that in dimension 1, you can really use the sort of chain structure, and so it was very convenient. So then they would just wave their hands and say, yeah, maybe in higher dimension we could try to do the same, but yeah, it's kind of more difficult. Let me see. Yeah, so we hope to identify f such that Fn goes to f. And then once you know this, you can verify that. So it's a general fact, which we are going to justify in a minute, is that if you look at the point of differentiability of the limit, then the derivative of Fn converges to the derivative of f. So really, it's not just we're hoping to get the derivatives later. Like you can show in advance, using the convexity of these functions, that if you know that Fn converges to f, and if you're at a point of differentiability of the limit, then the derivative of Fn converges to the derivative of f. Okay. Say again? At the point of differentiability, yes. Yeah. Yes, thanks. Okay, so for the Ising model, in fact, you can justify kind of by abstract arguments that indeed this object will have a limit, because you can do some box decomposition and use some sort of approximate subadditivity or something like this, and so you can know in advance that indeed this will happen. Well, then the question is, really, can you compute it? Because this is the gist. And in dimension 1, indeed, this is what Ising did. But then it's more complicated. And the argument of Rudolf Peierls did not use this sort of approach. Instead, it was a perturbative argument that works for very large beta to show that there is a discontinuity occurring. But in the 40s, Lars Onsager and other people realized that they could also compute this limit in dimension 2. So let's say Onsager and others. So in particular, they could identify exactly what is the beta c and compute the limit here at beta c. And this really, in my opinion, is what made the Ising model so central to the theory of statistical mechanics, because then they had their first theoretical model to really study the phase transition, the critical behavior around the beta c. They could really just stare at this formula and see what it says. So in particular, they could ask themselves and answer questions like, what exactly occurs at beta c in this transition from functions like this to functions like this. So for instance, if you plot the graph at beta equals beta c, what does it look like? Okay, and they could show that here you will have a vertical slope like this. Whoosh. Yeah, not quite success in vertical sloping, but okay, fine. At beta equals beta c, they could determine exactly how it behaves around here. And they showed that the curve is like h to the power 1 over 15, I think. And this was really remarkable. Like they really realized that, in fact, so far their understanding of critical, they were not expecting this exponent, and they realized that they did not understand critical phenomena. There was really some problem here. They had to invent new things to try to approach this, because on this special example, where by the magic of these calculations, they could compute things explicitly, they could see that the exponents were really not what they were expecting. Okay, and also we build a toy model. This is spins on we do our grid, etc. It's perhaps a bit specific, but physicists expect, and I think everybody expects, that this exponent that shows up here is really universal. It does not depend on the small details of the model. The reason being that these are sort of large-scale effects, so the small details will be a bit washed out when this exponent comes up. Okay, another question they could ask is, if you're just a little bit above beta c, how does it look like this little gap? How does it start to grow? And similarly, they could figure out how this behaves. So let me try to plot this. Okay, so this is beta greater than beta c, but think of it as being small. And the gap that is opening here, I think they showed that this is beta minus beta c. I would say 1 over 8. Let's see if it's true. Yeah, that's true. And again, this was a surprise, and they were very interested in understanding this, trying to understand this better. Okay, and now you can ask also about higher dimensions. So it so happens that, so now I'm going to just describe what we know about this from much further studies, okay? About these exponents. So in very high dimension, things get simpler again. So later we're going to introduce the Curie-Weiss model, where instead of the grid, you do your problem is set on the complete graph, like everybody interacts with everybody else. And when you go to high dimension, in some sense, it behaves a bit like this. And so they could convince themselves that in high dimension, maybe I'm going to take another color. I'm going to make sure I don't make mistakes. This instead becomes 1 over 3 in high dimension. And this instead becomes a 1/2 in high dimension. And so soon we're going to study this other model, the Curie-Weiss model, which I claim displays the same exponents. And I'm not going to do all of the steps towards explaining that these are the same exponents that show up for the Curie-Weiss model, but we're going to compute the free energy, and we're going to find an explicit formula. So then it becomes an analysis exercise to check what these exponents are. Okay, I think it's in the book actually, so you can also read it in the book. Yes, and then very high dimension actually means up to dimension 4. I think in dimension 4 there are some logs, but it's still with the same exponents in red. Mathematically, yeah, I think this is even shown mathematically. And I forgot the references, but they are in the lecture notes, so it's fine. And in dimension 3, we don't know. And personally, I don't expect even that there will be any decent description of these exponents. I think maybe one day we will manage to show that there exist exponents such that this is true. I don't know, maybe it's even known, I don't know. But yeah, there's no reason a priori to expect that we can always compute these exponents. In dimension 2, we managed to compute the free energy, but in general, there's no, it's not always possible to do this calculation.
Is there an intuition why it's so difficult to do it in dimension 3?
I think really the question is how come is it possible in dimension 2? And there I think, yeah, I don't know. I'm not very good at explaining this because also people have come up with many different proofs. Maybe nowadays people would point to conformal invariance properties, or I'm not quite sure what is the reason why it's possible in dimension 2. But for me, the mystery is why is it possible in dimension 2.
In some sense also, like in the physical community, when Onzaga showed that there was an explicit solution, that was a kind of a shock, because this Onzaga explicit solution is kind of magical. So everybody, like, he was able to actually compute the probability distribution. It was kind of, it was like,
yeah, that's my, I mean, I was, yeah, I don't know very well, but yeah, my impression is really the mystery is how come we managed to figure it out in dimension 2. Okay, so I think that will be it for the small tour of the Ising model. What I wanted to emphasize is that we see that if we can compute the free energy, there is really a lot of benefits that we can derive out of it, because then by taking derivatives, for instance, we learn stuff about the physical system. And well, for the Ising model, this is perhaps not the, if you have already followed the course on the Ising model, the calculation of the free energy was perhaps not super central, because except in dimension 2, we cannot do it, basically. But in the models I'm going to discuss later, we are going to be able to compute the free energy, and then, if you can do it, then it's really good. So this is going to be our focus. So maybe we're gonna take a short break before we switch to Curie-Weiss. But yeah, then we're going to focus on Curie-Weiss, and then there will be much more symmetries in the geometry of the graph. So here the lattice does not have a very large symmetric group. But if everybody interacts with everybody else, there's like this permutation invariance, and this gives us a bit more hope that we can compute it. So perhaps, I'm still kind of trying to answer your question, and I'm just saying, I'm saying, oh, it's really miraculous here that we managed to compute the free energy. But then I'm going to tell you, oh, we're going to struggle to compute the free energy in many models. But these models feel like we have a better chance because they have much more symmetries. So now we move on to the Curie-Weiss model. And this is a practice that physicists often do, that when things get complicated, maybe they try to explore other models. And here maybe the Ising model is difficult. For instance, if we want to understand it in high dimension, it's perhaps a good guess to think that it will look like a little bit like if the graph had even more connections. In some sense, it was just the complete graph. We ignore the geometry of the graph. Like, there's no more geometry hidden. There's no more lattice. Every spin interacts with every other spin. Let's see what happens in this case. I don't know very well what's the history of the Curie-Weiss model, actually. I tried to figure it out, but did not seem to be so easy. To me, at least. Okay. So perhaps, yeah, I should say, before I define the model, I should say that maybe I'm going to write like this. I should say, so it's clear that we're going to gain a lot by basically trivializing the geometry, because there will be so much more symmetry. This is clearly going to be beneficial for us. But I also want to point out that there are also a few things that we're going to lose. For instance, when I was discussing the Ising model, I mentioned very briefly that you can show a bit with abstract methods that the limit for energy is going to exist by using a box decomposition argument. You have your, in RD or in ZD, when you have a big box, you can think of it as being decomposed into a bunch of smaller boxes. And what makes this argument work nicely is that you make an error, but the error will be related to the boundary of the inner boxes. And as you make this dimension, this argument with very, very large boxes, the boundary will be a bit negligible in ZD. But then if you're on the complete graph, this becomes a little bit less clear. If you try to split the complete graph into two, then yeah, the boundary is kind of as big as the rest, and so. So anyway, just to mention, most things will be better, but okay. You cannot do box decomposition arguments anymore. All right, so the Curie-Weiss model, this is the first model we are really going to study. And it's a non-disordered model like the Curie-Weiss model. So what do we do? This was the energy for the Ising model, but with I and j being neighbors. Now I'm going to just sum over all indices. And since there's no more geometry, I'm just going to index the indices from 1 to n, because there's no more box. I, j, from 1 to n. So sigma, I should have said, is in +1 - 1 to the power of n. And I want to put a parameter, and for a reason that will be apparent later, instead of calling the parameter beta, I'm going to call the parameter t. It's perhaps slightly not great because beta is the inverse temperature and t evokes temperature, but keep in mind t is like inverse temperature. Okay, t, and then I divide by n in fact, because also remember that in the end we're going to, for instance, this is a set of size exponential in n, and we've already argued in the first lecture that it's good to keep the balance between energy and entropy, the number of configurations we have, to be comparable. So we want that ultimately when we take exponential of hn, hn is its maximal values are over the n. Okay, and you see that, for instance, if everybody is +1, this is going to look like n squared because I sum over every I and j from 1 to n. So if I want to keep this to be over the n, I have to make this division. Okay, and just like with the Ising model, we are going to also give ourselves this extra freedom to push the sigmas in some direction with some parameter h. Okay, so this is my energy function, and once I have written an energy function, I have a well-defined problem. I can try to study its free energy, try to understand what's going on with that. Make sense? Yes?
Why were you dividing by n in the Ising model?
Why was I not dividing by n? Because in the Ising model, I was writing, I wish I could write it there. No, I'm not gonna try. Do not try. In the Ising model, I was writing this, sum of sigma I, sigma j, I, j in the box, and then I neighboring j. And because they are neighboring j, so this will be over the volume of the box, which is the right order of magnitude. This is also the number of configurations. This is because there was this extra constraint that they have to be neighbors. Make sense? Yes.
So do we count sigma I in the first term?
Yeah, it's a bit silly, but yeah, I keep it there. Yes. Yeah, so it's a constant term. So like if maybe you already have this physics intuition. If you add a constant to the energy function, it's not going to change anything because we say the probability is proportional to exponential blah. So it's just going to add a constant here, but then we're going to make the division later, so it's fine. And when you do calculations, it's kind of convenient that you don't need to worry about distinguishing if I is equal to j. So that's why I say it like this. But it's true that it's a bit strange, maybe. But are there other questions or comments? All right. maybe this was an aside for easy. Should I? Let me see. Okay, so now let me write down the free energy for this model. So 1 over n log sum over sigma in plus 1 minus 1 to the n of exponential of hn t h sigma. So you see now I've put all of the parameters in the h, like t and h. Yeah, I should have said t. I think of it as being non-negative and h as being a real number again. Okay, just like for the easy model.
The free energy does depend on sigma?
Good point. That is clearly a mistake. Thanks a lot. Yes. Other things to say? Good. Yeah. So I want to, I left a bit of space here because I want to change a tiny bit this expression. I want to divide by 2 to the n here. So you see it's really not changing anything. It's just changing the free energy by a constant. You use the properties of the log. You see there's just a log 2 that is added or subtracted depending on if it's there or not there. The reason I like to do this is that then we can really interpret this part as being some expectation. It's really averaging over sigma being Bernoulli's, okay? And so it's kind of intuitively pleasant to set it up like this. All right, and now you've seen me struggling with writing Gibbs averages with very long expressions on the Ising model. So now I'm going to give myself shorthand notation for this. Maybe I'm going to squeeze it here. I'm going to write like this. So with the bracket, when I write f of sigma bracket for some, f maybe is not a good name choice. G, let's say, h. H is not a good choice either. Good point. G was not so bad after all. By this I mean, so here I think of this as being an expectation and sigma as being the random variable that is sampled according to the Gibbs measure. So if I write it explicitly, it means I do the sum over all configurations of g of sigma exponential of, hn t h sigma divided by the normalization, sum over sigma exponential of hn t h sigma. Good. Okay, so be mindful of the fact that this averaging depends on your choice of the parameters t and h, and n also actually, even though I'm not displaying it in the notation. But hopefully it will be clear all the time where these parameters are. It's good? You can see at the back? More or less, yes, good. All right. So the key thing that makes this model really easy to study is that in fact I can rewrite this function entirely as a function of the sum of the sigma I. So observe, it's like the little miracle of the Curie-Weiss model is that hn of t, hn sigma, I can rewrite it as just, how should I write this? Maybe I'm going to write this. 1 over n sum of sigma I squared times nt plus h sum of sigma I. Okay, and if I had removed the diagonal part, then I would just have a small error term, but that would be fine. And so basically, it's just a function of this guy. So if I understand this guy well, I claim we can understand the behavior of this free energy. So let me try to convince you of this. Okay, maybe a reminder. This large deviation thing that we saw last time. So we can write a large deviation principle for this sum of sigma i's under this IID measure, which is just the sum of the Bernoullis. So I'm going to try to write this. Tell us that is Cramer's theorem that we saw last time. So instead of writing expectations, now I write explicitly this sum like this, so that we don't confuse each other. We don't confuse ourselves on this. But here I'm writing basically the probability that this average magnetization sigma I is about m. So I'm writing the large deviation principle a bit informally here, but okay. What this was telling us is that this is approximately exponential of minus n times psi star of m, where we can explicitly write what psi star is. Trying to think what was my... Okay, so psi star of m is the convex dual of the function psi, which is the, let's say, log Laplace transform of one of our Bernoulli random variables. So it's, the expectation of exponential of lambda times this random variable, which I can rewrite as logarithm of the hyperbolic cosine of lambda if I wish, but whatever. I mean, this is what it is. Okay. Now, in fact, here I'm quoting this large deviation thing, which I told you about extensively yesterday. But this is, in fact, a rather simple thing to observe because this is just a combinatorics question. You have a bunch of plus ones and minus ones. You're asking about the number of configurations such that, you have just the right number of plus ones so that the average is equal to m. So basically, you want a proportion of 1 plus m over 2 of plus ones and the proportion of 1 minus m over 2 of minus ones. And so then you can write the combinatorics and use Stirling's formula, and you will get this result. Okay, so you can do this little exercise if you don't know what to do. And or just to verify that large deviations give you the correct formula. And in particular, if you do this calculation, you're going to have a more explicit expression for psi star. But here you can make the calculation here. You can just replace psi by what it is and try to figure out a nicer looking expression. I'm going to write it. M plus 1 over 2 log m plus 1 plus m minus 1 over 2 log m minus 1. And if this is all very well known for you, you can also think about why it makes sense that what shows up here is the relative entropy of the tilted Bernoulli with respect to the centered Bernoulli. Okay? Yes?
So on left-hand side, you mean the probability of the
Left-hand side. Here? Where? Here?
Yeah, on left-hand side, you mean because you write that. You mean expectation or?
But this is expectation. This is a bizarre symbol for expectation of indicator function of that event. So this is the same as probability of that event. Right? It's just that instead of writing expectation, I write explicitly the 2 to the minus n sum blah blah blah. Yeah, it's a bit confusing, but okay. Does that make sense? Or thanks for the question. Yeah, if everybody finds that that this is faithful to large deviations up to the These are unequal, like approximately equal signs. Good. Okay.
Sorry.
Yes.
So this is expectation with respect to the uniform measure.
Yes, exactly. Yeah, but you're saying we've seen. But the uniform measure is the same as the Bernoulli. No, this is really sampling. If I tell you compute the expectation under the law where each sigma is sampled as a Bernoulli +1 - 1 center, this is that, right?
Yeah.
And so that's what I'm using. I'm using that there are IID random variables, and so I can apply Cramer's theorem.
Okay.
That makes sense.
The Gibbs measure, so does it have much meaning here? Or
Yeah, so we're not yet there. I'm just preparing the ground for calculating the free energy.
Okay.
Yeah, I'm saying that because we know how this behaves like this, we're going to use this as a tool to compute that object and then to deduce what, like properties of the Gibbs measure. Okay. Yeah, good point. That's why it's confusing. So this is not the Gibbs measure, but it's part of the plan. We're going to use that result later to calculate this and then to deduce stuff about the Gibbs measure, yes?
Just 1 minus n.
Yes, thanks a lot. Thank you very much. So maybe I could plot it. So it's 0 at 0, and then it has a vertical asymptote. The tangent is vertical at 1 and -1, and that's the shape.
And it's plus infinity.
And outside of this interval, it's plus infinity, which makes sense because if you're hoping for this guy to be, 2, it's going to be very difficult. Okay, yeah, so I'm explaining this because now you see what we want to compute is something like this, where this is only a function of that object. And in some sense, we understand the size of the level sets of this function perfectly in some sense using this formula. So we can then plug it into that calculation and figure out what is the free energy. Okay, I'm going to gesture at why this is true right now, and hopefully.
A contraction principle, no?
Yes, but I'm going to do it kind of by hand in some sense.
Yes, exactly.
Yeah, so let's now clarify why I thought this made sense to explain. So I'm thinking that maybe I should give a name to this thing. Let me call that guy here Sn of sigma. Okay, or this guy also here, Sn of sigma. Okay, this is the random variable of which I made a large deviation argument. So let me rewrite the definition for this guy. Fn 1/n log sum over sigma of exponential Tn Sn squared plus Hn Sn actually. Say again?
Before there was a division by 2 to the n.
Oh yes, you're right. Thanks. Thank you. Have to explain this nicely. Maybe I'll. Okay, this is the definition. Let me give you a lower bound on the function. So I could just restrict myself to those configurations sigma that satisfy this property, okay, just as a starting point. So suppose I compute this instead, 1/n log 2 to the minus n sum over sigma, such that Sn of sigma is approximately equal to m of exponential Tn, maybe I should write like this, n Tsn square, and let me drop the argument. Then this, I'm doing only the calculation informally, but you see if I restrict, then I can substitute here and write m square and m. Okay, so this is basically m square. This is basically m. And then I'm just counting the number of configurations like this, which I know the answer of. Okay, so this is going to be approximately, let me just now flush everything through the log. You see what I'm doing? Right, this now I know what it is exactly. I'm counting this number of configurations satisfy this, and it's given by that answer, okay, minus n psi star of m. So overall, this is going to be approximately Tm square plus Hm minus psi star of m. Does that make sense, or was that too quick? Are there questions on this, or it makes sense? And you see that I can allow myself a little bit of wiggle room with m. Like if I make if I give myself an epsilon, I can just think about configurations that are approximately up to epsilon error near m, and then I only mess this up by an amount of epsilon. But if I give myself an epsilon of room, m can only be really between -1 and 1. So there's only a finite number of possible m's, basically. So in this sum, I can just split it into essentially a finite number of terms like this. And I have just, before I take the log, it's going to be a sum of exponentials with this parameter, with m varying between -1 and 1. So essentially, as n goes to infinity, you're just going to want to pick the m that maximizes this quantity. Okay, so let me write this as a proposition. We have, for every t and h, fn of t h converges as n goes to infinity, to the supremum for m between -1 and 1 of t m square plus hm minus psi star of m. Okay, I only sketched the argument very briefly, but you see what you have to do. Well, you're going to, if you want to write the proof, you're going to decompose it into a lower bound and an upper bound. The lower bound is really essentially what we have done already. You can just pick for each m, you can lower bound by this, and it gives you the correct thing. So the lower bound, essentially, we wrote it down. And for the upper bound, you have to do this decomposition of the interval into a number of pieces, which you keep finite, but kind of, numerous. Does that make sense, or? Let me erase.
You see, the point is like passing from the sum over the whole set to passing from the sum on the smaller pieces. So how do you?
So imagine I have I decompose my interval -1, 1 into, 10 pieces.
Okay.
Then I can say, each configuration is going to have Sn of sigma fall into one of the 5 pieces. And so this gives me a partition of the set.
Okay.
And then I run the argument in each of the guys. And I just have a small error maybe of the epsilon. This is not exactly m, but it's m up to epsilon error. And so I can say that this is true up to epsilon error, and that's good enough for me. Okay, so the proof is in the lecture notes, of course. What I would like to do now is to convince you that indeed, once you know this, you can really understand the limit of the derivatives also, because I motivated the whole thing by saying derivatives are nice. Did I do the calculation? I forgot. Maybe I should have mentioned that again when we differentiate with respect to h, this guy. Did I say that? Maybe not. What we get is going to be the mean of Sn of sigma. Let me just rewrite it again. dh Fn of T and h is going to be the average of 1 over n sum of sigma I. Okay. And if I was differentiating with respect to t, I would get the average of Sn squared instead. In particular, keep in mind that this is between -1 and 1. And also, if I differentiate with respect to t, it's even between 0 and 1. So all the functions we're dealing with are Lipschitz uniformly over n, with Lipschitz constant bounded by 1. So in particular, if you want to... So here we identified the limit directly, but you can know in advance that you can extract subsequences because they are Lipschitz. And I could have said also that when t equals 0, the function is very simple because this is, okay, maybe I'm not going to say it, but you can really know in advance that you can extract subsequences out of this. Okay, so what I want to display now is that indeed we can conclude that, let's say most of the time, the limit of this guy will be the derivative of the limit. Let me give a name to the limit, f of t and h. So let me write this as a proposition. If f is differentiable at th, then, well, in fact, I could say, if I wanted to be a bit more precise, if f is differentiable in h at the point th, then the derivative of fn converges to the derivative of f at th. And so then we recover the information about this average. All right, let's do a real proof for once. I'm going to write the following: fn of t h plus h prime. So what I'm going to use is that the function is convex. Maybe I should emphasize why this is true again. In the second, like in the last lecture, when I introduced the log Laplace transform of a random variable, we showed that this is a convex function. And I pointed out it's even jointly convex. And here you see that it has the correct structure. Again, this is non-standard notation, if you like, but this really is an expectation, as we discussed. So this is expectation of exponential of t times something plus h times something. In other words, vector th dotted against some variable. And then we take the log. So this is convex jointly in t and h by this argument we saw last time. Okay, so it's Hurler's inequality. And this is what I want to use in this proof. So I'm at my point of differentiability of the limit, like th, and I perturb the h argument a little bit, and I use convexity here to say that this is greater than fn of th plus h prime times the derivative. Okay. And now, as we observed, this guy, we don't know yet it converges, but in any case, it's a number between -1 and 1. So at the worst, I can extract a subsequence and have convergence along a subsequent to something. So say that dh fn of th converges to p along a subsequence. Okay, which again I'm allowed to assume because this is between -1 and 1 all the time. So there is some p, I can find a subsequence and I can find a p such that this occurs. And now if I pass to the limit n goes to infinity in this expression along the subsequence, what we get is that f of t h plus h prime is greater than f of t h plus p h prime. And this, I should have said, perhaps a bit more nicely earlier, is that this we're writing for every h prime in R. Okay? But the assumption that we have on f is that it's differentiable at th. So this itself is f of th plus h prime times the derivative plus little o of h prime as h prime goes to 0. And now when you have this comparison, you have, up to lower order, you have two affine functions, one being above the other. The only way this happens is that the slopes agree. Okay? Otherwise, you will have a problem. Okay, so notice also that for this argument to work, it's important that you can take h prime small positive and also small negative, because otherwise you will have only one inequality. So we conclude that p is equal to the derivative. And that's it. That's the end of the proof, because as we said, this is a pre-compact sequence. So if there is a unique limit, then we are done. Okay, and I stated this proposition specifically in the context where we were embedded into. But please notice that what I'm really using in this proof is the convexity of the functions, and perhaps a little bit that there are Lipschitz also. And this I could weaken a lot, but really what is making this work is the convexity property of the functions. And even this I could weaken, but okay, fine. So I'm going to use that thing later, or at least refer to it. As soon as the function is convex, or even you can estimate from below the second derivative or something. Okay, as soon as the function is convex, you can conclude that at points of differentiability of the limit, the derivatives are going to converge to one another. Okay. So now that we have all this, really, as far as I'm concerned, I consider that we have solved the Curie-Weiss model, because we have written down explicitly the free energy, and we have guaranteed that next we can recover information about the average of the Gibbs measure using this simple principle. So, but okay, I'm not gonna. Let's see a little bit how this will feel like when we do this. Psi star of m, I drew a picture of it earlier. Near m equals 0, it looks like a parabola. So if you plot this function and it's a parabola going upwards, so let's set h equals 0 and plot this function of m for different values of t, just to see how it looks like. So for t small, this function, this will be a parabola also, but t is small, so it's not going to manage to compensate for this guy wanting to also be a parabola. So I did not do my axis very nicely. Because mostly it's going to look like this, a parabola going downwards. Because this is for t small. I'm plotting the function m maps to t m square minus psi star of m. Okay. And so the optimum when h is 0 is going to be here. And if you put h positive, it's going to be a little bit tilted to the right or to the left, but not much will change. Okay, you will just have a little tilt. But now, when t is large, this parabola, this tm square, is going to become the dominant part. So near 0, you will have indeed that it's going up like this. Okay, and then we've seen also that the psi star has vertical slopes at the end of the interval. So at some point it has to bend in the other direction. So it's going to be like this. Okay, I don't know where it goes exactly, but this is the shape of the function. This is minus 1 and 1. Sorry, 1. And so at h equals 0, if you want to maximize this function, in fact, you have two choices. And you see that as soon as you tilt h a little bit positively or negatively, you're going to prefer this one if h is positive or this one if h is negative. So it's going to change a lot which optimizer you prefer when you bend h towards the positive or towards the negative. And the consequence of this, whoops, maybe I'm using this just to maybe I don't erase this formula. So anyway, this is to give you a picture of how how the function, the limit for energy will look like. And perhaps I should say one more thing, which I think should be like common knowledge, but unfortunately I don't think it's common knowledge. It's the envelope theorem for, so how do you compute derivatives of problems like this? You have a supremum, blah, blah, blah. I want to know properties of the derivatives of an expression like this. So I claim that as soon as that object, this function f of t and h, is differentiable at a point of interest, the derivative of f will be what you get if you just forget about the supremum, just substitute for the optimizer in the m, and differentiate naively. So if let's say, if m of th is an optimizer, and th is a point of differentiability of the function, I could say, yeah, in particular, if there is a unique optimizer, then this is differentiable. And what you get is that the derivative, so then the derivative of the function is what you get if you naively differentiate. So if I naively differentiate with respect to h, I just get m. Okay, so I claim that then this is m of th. I say this because I want to explain that we expect that the choice of the optimizer will have this discontinuity here. For h strictly positive but small, it's here. For h negative and small, it's here. So the derivative of our limit for energy is going to jump from being that value here to being that value here. Okay, so if I plot it, well, for t small, nothing changes. I mean, everything is kind of smooth. So the derivative, the function will look kind of like this. I don't know. This is for t small, and I plot h maps to f of th. But for t large, we will have a discontinuity in the derivative of this function. So, okay, so the point is that here it looks like the absolute value. And then it's a convex function, and it's even though my drawing does not make it clear. Sorry, h. Okay, and here, the mean magnetization, then it's the derivative of this function. So we recover the drawing that we were having for the Ising model. Here, the derivative is varying progressively without discontinuity from being -1 to being +1. And here, the derivative is varying, it's -1, and then it's starting to increase towards 0. But then suddenly it has a jump, and then it's going towards +1 again. Okay? And in fact, the derivative is the optimizer, so yeah, I'm really, the derivative is just following this loop. All right.
In case the function is not differentiable, we can use sub-differential, and the discussion is basically the same, no?
Yeah, except this is not necessarily going to converge. I can say that it's going to belong to the convex envelope of the set of subdifferentials. Yeah, I can say that, but okay, fine. Yes. Yes, and again, you see that there is an advantage to focusing first on the free energy because as I tried to anticipate earlier, it's more robust to, there is less difficulty. It's well defined for every t and h. It doesn't depend too much on the details of the model. If you were trying right away to study the derivative, like the mean magnetization, well, there are some points where it's kind of touchy. It's a difficult thing to figure out exactly what it does. Like at h equals 0, the statement that I've written here does not tell you what the mean magnetization becomes. So in this specific instance, you know that by symmetry it should be 0, but yeah, that's just okay. So maybe in the last few minutes that I have, I want to, yeah, maybe this is going to be a bit short. Okay, let's see. I want to consider also generalizations of the Curie-Weiss model that we can similarly resolve like this. So I want to just keep those few properties of the Curie-Weiss model that allowed us to solve it. So let's say this is a 3, a generalized Curie-Weiss model. So in the definition of Curie-Weiss, we had this T n 1 over n sum of sigma I squared in the energy. And I want to allow myself to replace the square function by any function. Okay? This is the first simple move we can make to get a larger class of models. So instead of postulating it's the square function, I want to think that it's just a generic function I'm going to call psi. And instead of this Bernoulli sampling that we were doing, now I'm going to finally use really expectation notation, or at least to emphasize more that we're doing some expectation calculation. I'm going to give myself a family of probability measures. I'm going to denote them at Pn. And when I want to do this, I'm going to write integral of blah, 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 dPn of sigma. Okay, so I give myself a Pn. Pn probability measure on Rn. And I'm going to want to keep things not too crazy. So I want that under Pn, when I sample from Pn, the sigma is not too large. I still have a bound, so I assume that the norm of sigma is bounded by square root of n dPn almost everywhere. Okay? The support of Pn is within this ball. Okay, I claim that we can write a modest generalization of the statement we have just obtained here. And you may wonder why I do this, but it's going to be very interesting later when we try to develop our PD techniques to have a broader range of models than just the Curie-Weiss model, because the Curie-Weiss model has a few more specificities that will not be present for the general case. So if I do these modifications, what I want to compute now, instead of my new free energy for this generalized model, will be something like this. So 1 over n log integral of exponential of t n psi of 1 over n sum of sigma I plus h sum of sigma I dPn of sigma. Sorry, so this is the definition. Maybe I should not have written a proposition yet. And now proposition. So, okay, so I want to claim that we can figure out the limit of this thing. And the second ingredient I have to make sure of is that I understand how this behaves when n becomes very large. And what we really want to have is that we know the large deviations property of this sum of sigma I under the measure Pn. Okay, so we have to know in advance what the log Laplace transform of this guy under Pn is doing. Right?
Sorry, I'm a little confused. Where does the sigma live here?
So sigma is in Rn now, so this is an integral over Rn. And this replaces the sum over sigma in the hypercube that we were having before. Does that make sense? Yes. Does that make sense to you also? Maybe not.
You write some sigma I.
So this part, sorry. So this is I from 1 to n. I'm sorry, I misunderstood. This is I from 1 to n. Sigma is in Rn. It's a vector of sigma 1, sigma 2, up to sigma n.
Oh, n is the dimension. Okay.
Yeah, and Pn used to be the tensor product of this Bernoulli measure. Does that make sense? But here maybe it's no longer a tensor product. And what I wanted to describe here is, as an assumption, we just gonna put that the log Laplace transform of sum of sigma I under Pn converges to something. And the log Laplace transform is already kind of written here. I just said t equals 0, this is what it is. Okay? So my assumption will be that fn of 0, h converges to something. Maybe I'm going to call it psi of h, as n goes to infinity. And that psi is a C1 function. Okay, so this is the hypothesis I put so that I know that I can have a large deviation principle for sum of sigma I under Pn, just like we had a large deviation principle for sum of sigma I under the Bernoulli measure just before.
Don't I assume convexity?
This is by definition, this is a log Laplace transform of of t some variable. So we have convexity of this object just by definition. Does that make sense? Okay, it's still the same structure with some expectation of. Is that clear? Yeah, good point. This is jointly convex in T and H. Okay, so we assume this. Once we assume this, then we can conclude exactly as before that Fn of T and H converges as n goes to infinity to the supremum over m of T psi of m plus hm minus psi star of m. Okay, where psi star is the convex dual of psi. Yeah. Yes. Okay, maybe I should have written h, but okay. So I think I'm running out of time. So I claim that this is really, if you think carefully about the argument we have done for the standard Curie-Weiss model, and you also remember the large deviation principle we saw yesterday, this just fits perfectly. The pieces fit together, it just works. And okay, I didn't even write where the m is living, but here I wrote m between -1 and 1. This was not absolutely necessary for me to write because when m is not there, psi star is plus infinity anyway. So I could also write m between -1 and 1 here due to this constraint that I've put here, but I don't have to write it. I'm just gonna leave it like that. So that was a bit quick with the generalized version. I apologize for this. Is it still kind of okay, this part, or is it still also okay, the rest, actually? Yes?
Sorry,
Yes?
just explain briefly, like the assumption of Fn0 H going to...
Yeah, this is the part I was quickest over, so let me just go over it one more time. In the case of the Curie-Weiss, I did not pay close attention. I was like, yeah, it's sum of IID, we can use Cramer's theorem. But really, what we saw yesterday is we need the convergence of the log Laplace transform of the variable. And the variable is this Sn of sigma. It's the sum of sigma I, really. So we want to know that when I take the expectation for respect to Pn of the exponential of some coefficient times some of sigma I, and then we take the log and we divide by n, this converges, and that is what this is doing. So if this occurs, and if this guy is C1, then I have my large efficient principle, and so I can run the same argument and I get the result. All good? Yeah, and we see that it's quite useful to think about this model later when we play with PDs, so I want to have this also in our, let's say, pocket. Okay, if there are no more questions, then I'm already a bit over time, I think, so thanks a lot for your attention.